In modern air warfare, the runway has become a vulnerability. For decades, air power depended on long concrete strips, fixed bases, and predictable launch points. But in a world of precision missiles and satellite surveillance, those fixed locations are the first to be targeted. So what happens when an aircraft no longer needs a runway? What happens when it doesn't even need a pilot? Welcome to the XBAT, one of the most ambitious autonomous combat aircraft concepts emerging in 2026. This isn't a disposable drone. It isn't a remote-controlled aircraft waiting for human input. It represents a shift in how air forces think about survivability, deployment, and decision speed. Traditional aircraft development often takes decades. Large defense contractors move through long procurement cycles, prototype phases, and multi-year testing programs. XBAT comes from a different philosophy. Designed using a digital engineering approach, much of its early testing occurred in simulation before physical prototypes were ever built. Billions of virtual flight iterations shaped its aerodynamics, software logic, and mission profiles. But the most important difference is autonomy. There is a major distinction between automated and autonomous systems. An automated aircraft follows pre-programmed routes. An autonomous aircraft adapts. If communication links are disrupted, XBAT doesn't freeze or return to base blindly. It continues operating based on onboard decision systems. This capability is powered by what its developers call an advanced AI flight and mission architecture, a system designed to interpret terrain, threats, and mission objectives independently. In a contested electronic environment, that independence matters. One of the most disruptive aspects of the XBAT concept is its ability to operate without traditional runway dependence. Historically, vertical takeoff aircraft sacrificed range and payload to achieve lift capability. The Harrier and F-35B, for example, trade fuel capacity for vertical lift systems. XBAT aims to challenge that trade-off, with an estimated long-range operational capability exceeding many traditional fighters. It suggests a new model, distributed launch points instead of centralized air bases. Instead of relying on large airfields, aircraft could operate from reinforced pads, ship decks, temporary expeditionary sites, remote coastal zones. This aligns directly with the U.S. military's Agile Combat Employment (ACE) doctrine, dispersing aircraft to reduce vulnerability. In a high-threat environment, survivability isn't just about stealth, it's about unpredictability. Unlike lightweight UAVs powered by small commercial engines, XBAT is built around a military-grade turbofan class engine concept. Using a proven engine core provides several advantages: established supply chains, known reliability metrics, easier global maintenance support. But propulsion is only part of the equation. Modern combat aircraft are power-hungry machines. Advanced radars, electronic warfare systems, and onboard computing require substantial electrical output. In many ways, XBAT functions as a flying data center. High-output generators transform it into an airborne node capable of powering sensors and electronic systems continuously. In 2026, air combat is as much about data dominance as speed. Altitude remains one of aviation's greatest advantages. Operating above 50,000 feet dramatically increases missile kinematic range and reduces aerodynamic drag. From that altitude, an air-to-air missile launched downward carries more energy and extended reach compared to one fired at lower levels. Without a human on board, XBAT isn't limited by pilot G-tolerance or life support systems. It can optimize flight envelopes purely around structural capability. That means sustained high-performance maneuvering without biological constraints. This changes engagement geometry, it changes endurance calculations, and it changes risk allocation. In a peer-level conflict scenario, fixed infrastructure becomes a liability. Large bases are visible from orbit. Missile trajectories can be pre-planned. XBAT's concept flips that equation. Imagine an aircraft stored in modular units, transported via containerized systems. deployable from dispersed launch points. Instead of defending a handful of known airfields, an adversary would have to track hundreds of potential launch zones. This dramatically complicates targeting strategy. Survivability through dispersion, not invisibility, becomes the advantage. Perhaps the most controversial and transformative element of XBAT is its autonomous decision framework. In traditional air combat, human reaction time governs engagement cycles. An experienced pilot might react in fractions of a second, but advanced AI systems can process environmental inputs in milliseconds. XBAT's system is designed to evaluate threats, calculate optimal maneuver paths, prioritize objectives, adapt without external communication, and importantly, if one aircraft adapts to a new scenario, that data can be distributed across the fleet. This creates shared learning architecture. Instead of individual experience, the fleet evolves collectively. This concept mirrors distributed computing, but applied to air combat doctrine. XBAT isn't meant to replace manned fighters. It's designed to complement them. Under the Collaborative Combat Aircraft (CCA) model, a single human pilot in an F-35 or future sixth-generation platform could coordinate multiple autonomous wingmen. That pilot becomes a mission commander rather than a sole operator. The unmanned platforms extend sensor range, carry additional munitions, provide electronic support, operate in higher risk zones. This multiplies force projection without increasing pilot exposure. Instead of one aircraft versus one aircraft, the equation becomes one pilot managing a distributed formation. XBAT appears designed for modular configuration. In stealth mode, internal bays preserve low radar signature. In high-capacity mode, external pylons allow increased payload. This adaptability reflects a key principle of 2026 Air Doctrine. Day 1 operations prioritize survivability and stealth. Day 2 operations prioritize volume and presence. Aircraft that can shift between those roles provide commanders with flexibility. The introduction of autonomous collaborative platforms forces adversaries to reconsider air defense calculations. Instead of engaging a limited number of expensive manned aircraft, defense networks must track numerous distributed platforms. Economically, this alters cost dynamics. Operationally, it complicates detection. Do autonomous systems replace pilots entirely? Unlikely, at least not soon. Human oversight remains central to strategic decisions, but operational tempo is changing. Decision cycles are accelerating beyond purely human reaction speeds. The XBAT represents more than a new aircraft. It represents a new philosophy. Fewer fixed bases, less centralized vulnerability, greater distributed autonomy, faster adaptive response. In the coming decade, air superiority may depend less on raw speed and more on adaptability. And that's what makes XBAT significant, not because it is dramatic, but because it is disruptive.